So, first law for open systems. What is an open system? We've gone through this. It's basically everyone here is an open system. You absorb moisture, you diffuse moisture, air. Basically, you're an open system, right? So it allows mass transfer across the system's boundaries. With an open system, mass transfer occurs, and energy transfer occurs in the form of internal energy, kinetic energy, and potential energy. In a steady flow system, there's no change in fluid properties with time. So there's no change in density. There's no properties change across. But also in steady flow, in this course, we'll be focusing on steady flow mainly. So we won't really cover unsteady flow. I'm just going to basically mention what it is. So, what is flow rate? And what are the units used to measure flow rate? Flow rate is it consists of mass, moles, or volume. It's the transfer of either in units, mass, moles, or volume across a system. And flow rate is basically the mass flow of a fluid across a single point. So imagine a plug of fluid moving across. So this plug going from here to here, and you measure the amount within that period of time. So your delta T in seconds, and that's your average flow rate. So your average flow rate is the mass over the change in time. Your plug in kilograms per second. Your instantaneous mass flow rate is the derivative of that. So at any one point, what is the flow of that plug? So that plug can speed up, that plug can slow down, that plug can change density, but that's an unsteady system. So in this case, in a steady system, if the flow is steady, then the instantaneous flow rate equals the average flow rate, because it's steady temperature, pressure. Yeah? So N is the total moles of a fluid passing a reference point, delta Ts, and the flow is steady, then the molar instantaneous average flow rate are also equal. At any one point, the same number of moles are going through the pipeline. And N will usually be in kilomoles per second, could be in moles per second, so pay attention, but in chemical engineering we usually refer to it in kilomoles per second. And for the volume of the plug, the volumetric flow rate is dV, the change in volume over change in time. And that is the volume over a specific time for a steady flow rate. So volume going through a pipe. At the same mass flow rate, two streams will have different volumetric flow rates unless their densities are the same. So if density is constant, you always have the same volumetric flow rate. But if density changes, or there are two different fluids, then your volumetric flow rate will be different. So if you have a temperature change, your system is unsteady, your density changes. Yeah. So imagine gas at 100 degrees and a gas at 200 degrees. Density change, hence the volumetric flow rate changes, but the mass flow rate is constant. So the unit is usually meters cubed per second. Mass is always conserved, so it's always, even if density changes, your mass doesn't change, so it just basically is less dense or more dense, but you have the same amount going through your pipe. moles are conserved when there are no reactions. So if there are two different components in your system and they react together, then your moles are not conserved. But if it's a single component or there is no reaction, you'll have basically the same amount going the same mass, the same moles. And volume is rarely conserved because density changes, temperature changes, the various different reactions. So many things can happen. So volume often changes pressure. The total energy of the system, the stream energy, equals the macroscopic internal energy plus the macroscopic kinetic energy of the system plus the macroscopic potential energy of the system. The macroscopic and the macroscopic. So, stream energy flow equals the total energy over the change in energy over time at any one point. Exactly the same as mass flow rate, exactly the same as mole flow rate. So, the total energy is the change in energy over time. And the energy flow will have units of energy per unit of time, so kilojoules per second or kilowatts. Hence, the total energy of component I equals the internal energy component I, kinetic energy plus potential energy. And looking at the internal energy first, you'll see the internal energy of a component. It's the mass of the component multiplied with the number of the internal energy, the molar internal energy, and hence the internal energy is the change, the macroscopic change of internal energy over T, and this macroscopic energy over the macroscopic energy of T is again of one component multiplied by mass times its molar internal energy. Because it's microscopic, remember it's microscopic. So for stream energy flow, if we substitute for the kinetic and potential energy, we get the following equation. Right? So kinetic energy, is the velocity. Let's start from the beginning. So the total energy is the stream's specific internal energy multiplied by its mass. Yeah, plus its mass times its velocity squared over 2, which is the kinetic energy, plus its mass times its potential energy, so gravity times the height it's moving. Height it drops, or the height it goes up, or the amount of head pressure. So dividing that equation by m, you can determine the specific energy content of that stream. So that is, it's a possible ways that energy is stored in any stream, entering or leaving the system. So these are all the potential ways that it can be stored in that way. So again, internal energy, kinetic energy, potential energy. So the heat is transferred into heat. So the energy is transferred into heat and into work, and this is transferred out. Right? So you have your inlet properties, your pressure, temperature, internal energy, your enthalpy, specific volume, velocity, Z, your height. Then you have your heat transfer, your turbine, and then you have your output properties, so pressure, temperature, again, internal energy, everything's conserved throughout the whole system. It's just you're compressing the system, yeah? And that requires input heat and output work. So the energy content of the fluid at the outlet is also equal, the E2 equals the outlet internal energy plus its kinetic energy plus its potential energy. Energy is conserved. Hence, the internal energy equals U2 plus kinetic energy plus potential energy. So you can put them in specific terms. So the energy at the inlet is the above equation, is the previous equation, and the energy at the outlet is our new equation. So going back to the first law of thermodynamics for an open system, the change in energy stored between the inlet and the outlet equals the energy exchange between the inlet and the outlet. So remember, energy is conserved. So E2 minus E1, the energy at the outlet minus, or rather the energy at the inlet minus the energy at the outlet equals the heat input plus the work input. For practical applications, this becomes E2 minus E1 equals Q plus shaft work plus fluid work, because you're compressing, so you have the whole work concept. So for fluid work, E2, the energy at the outlet, minus E1, energy at the inlet, equals Q plus work, shaft work minus fluid work at the inlet plus fluid work at the outlet. So you can rearrange that equation to become E2 minus E1 equals Q plus shaft work minus negative P1 V1 from your fluid work from yesterday, and plus P2 V2, again, fluid work from yesterday. Substituting for E1 and E2, you can put your previous equations. The internal energy plus kinetic energy plus potential energy equals Q plus work, shaft work plus P1 V1 minus P2 V2. Rearranging the fluid works, you have the internal energy plus P2 V2 minus U plus P1 V1 plus the kinetic energy plus the potential energy plus the kinetic energy of the inlet, potential energy of the inlet equals Q plus shaft work. So since enthalpy, this is so we can narrow it down, we can simplify that equation. We know that enthalpy is defined as H equals U plus PV. So we can replace that with enthalpy. And now it's your enthalpy change. Right? And we'll see why this is useful in the tutorial questions. That's why I want to teach from the tutorial questions. So your enthalpy change plus the change in kinetic energy plus the change in potential energy equals Q plus shaft work. The energy change is actually meters squared per second squared, and that's identical to joules per kilogram. And we can go through a proof for that if you want, but you can just use it if you wish. Also, something that's noted, you should make sure you pay attention to the units, to the dimensions. So a lot of the times you get your units in kilojoules per kilogram. So remember, to convert, it should be in joules per kilogram. Quite self-explanatory. So, taking all the terms to the right-hand side, you can define it as a finite equation. So, Q plus shaft work minus changing enthalpy minus changing kinetic energy minus changing potential energy equals 0. Now, if the system equals 0, it's a steady system. So if the sum is 0, it's a steady system. And remember, the mass flow rate is in kilograms per second. So, and because it's a steady system, it will be the same as instantaneous. Okay. So if we do an energy balance, the quantities, the quantities are energy flow per kilogram, because the previous ones are in moles. So the mass times the Q, the heat, the molar heat, times the shaft work, the molar shaft work, MWS minus mass flow times change in enthalpy minus change in kinetic energy minus change in potential energy. You can redefine it in this term with capitals, so it's for mass flow. Okay. And this is for, again, steady state. So one is inlet and one is outlet. So you have an inlet, outlet, steady system. So we can generalize this a bit further. So the sum of all the actually you guys are doing programming at the moment, right? Visual Basic, right? So if you're writing a Visual Basic code, for example, you have 5 components: I, J, K. Usually you put like that. So you have, let's say you have 3 components: I, J, K, and you want to do the sum. So that's how you do a for loop. So the mass of component I multiplied by the enthalpy of component I, plus Q plus double work equals the sum. So I, J, K. That's why there is a sum. Since the change in kinetic energy and potential energy are considered negligible in steady flow, we can, and there is no heat or work in steady flow, we can remove them. So you have mass times enthalpy equals the sum of mass times enthalpy of component J. Inlet, outlet. Again, just try to follow, and we'll go through the tutorials. So enthalpy balance for the streams is mixed or separated, so there is no energy exchange. So you have a single pipe, you have a single flow, there is no exchange, or there is no mixing, there is no separation, it's just a simple flow. That's your energy balance for such a system. So we know that enthalpy for ideal systems are only dependent on temperature. So the change in enthalpy equals Cp, heat capacity at constant pressure, in regards to change in temperature. Assuming constant Cp, because ideal situation, we can take that out and drive the equation for enthalpy, Cp multiplied by T2 minus T1. This is used for one stream in and one stream out systems, and reference temperature is based on the inlet. So when you're looking up steam tables, always you start from inlet temperature. Have you guys used steam tables before? Yeah. So enthalpy of component I and you integrate Cp dt in regards to Ti and T reference, this is used for multiple stream systems. So reference temperature is your T reference, and usually based on one of the inlet streams, whichever is convenient. So if you have multiple components and you need to do multiple derivatives. So let's start with a heat exchanger. You have your stream 1 going in, you have your stream 2 going out, and you have your heating fluid. In this case, let's say heating fluid, it's a heating system, so you have hot steam coming in and you get cooler steam coming out. So for large quantities of heat exchange, the change in kinetic and change in potential energies infinitesimal. It's too small to consider. So we can assume shaft work is 0. Because there is no movement, there's no piston, there's nothing. So Q minus change in enthalpy equals 0. And hence Q equals mass times molar enthalpy. So if you have your molar enthalpies from steam tables, and you have mass flow, you can calculate the amount of heat. And you'll use that in heat exchanger design, the tutorials. Heat and work are transferred. So for a reciprocating compressor, we know that at low speeds and low gas throughput allows the gas to cool. So because you're operating at low speeds, plenty of time, plenty of heat exchange with the atmosphere, so it's going to cool. Or you can have water cooling systems. But it's never going to be enough in the real situations. So again, we can consider kinetic and potential energy to be negligible in this case again. And you have shaft work. So Q plus shaft work minus the change in enthalpy equals 0. And hence Q plus shaft work equals mass times change in enthalpy, molar change in enthalpy. Now the reason there is no or change in kinetic and potential energy is negligible is because there is cooling. And it's low speed, so it's steady. Most pumps and quite a lot of compressors operate almost adiabatically. And again, we can consider the change in kinetic and change in potential energy to be negligible. And since it's adiabatic, Q equals 0. So there's no change, and there's no exchange of heat. Again, remember, best insulation in the world. So for adiabatic systems, the shaft work minus the change in enthalpy equals 0. And hence, shaft work equals mass flow rate times the change in molar enthalpy. Knowing temperature and pressure and the outlet pressure, you can calculate T at 100% efficiency. So you calculate shaft work, you calculate enthalpy, you have your mass flow rate, you put in your pressures and temperatures in your shaft work equation, you can calculate your new pressure. And knowing the power, you can also calculate temperature, because you know if you know the amount of shaft work, you have your mass flow rate, you have your enthalpy, you can calculate temperature. In isothermal compression, again, the change in kinetic and potential energy are usually negligible. So for ideal gas, the change in enthalpy is a function of temperature, and the change in temperature equals 0, because it's isothermal constant temperature. So your Q equals minus shaft work. And these are equal quantities of heat and work exchange in opposite directions. So you have your heat and you have work, and they're always in opposite directions. And for polytropic compression, your Q, your input energy plus shaft work equals mass times change in enthalpy, molar enthalpy. So these are significant quantities of heat that are exchanged. Hence, the polytropic work input is usually more than isothermal, but less than adiabatic because of exchange of heat. So for open systems and adiabatic processes, starting from an adiabatic process, we know that P1V1 to the power gamma equals P2V2 to the power gamma equals a constant. So applying this to open systems, it only involves state variables. So the first law for an open system is Q plus shaft work minus change in enthalpy minus change in kinetic energy minus change in potential energy. Remember what happens to kinetic and potential energy in these situations. So adiabatic change in kinetic energy and potential energy is negligible. Hence, shaft work minus change in enthalpy equals 0. Shaft work equals mass times change in enthalpy. You've seen that before. So this can be written as shaft work equals change in enthalpy. In differential form, the change in a shaft work equals change in enthalpy. If the differential shaft work is the change in shaft work equals change in the volumetric flow rate multiplied by the change in pressure. So the amount of pressure that is required for the amount of work. Its volume term is the volumetric flow rate, usually in meters cubed per second, and its overall units are in watts. So substituting into the first law, you have volumetric flow rate multiplied by change in pressure equals the change in enthalpy. And remember, molar heat capacity of an ideal gas, change in heat enthalpy over molar enthalpy over the change in temperature equals Cp, the constant pressure heat capacity. So the change in enthalpy equals Cp dt, and the change in enthalpy, the mass enthalpy equals Ncp dt. And if the lower expression is substituted in the upper, then the conditions for an ideal gas open system following an adiabatic process will have been satisfied. So we'll just see that. So if you substitute that, and you know it's an ideal gas system, so nRT over Pdp equals Ncp dt. And if you take, if you just separate the terms for E's, R over Cp, so you know so you have R over Cp multiplied 1 over P dP equals 1 over T dt. So integrating that is quite simple. At this point, R over Cp log of P2 over P1 equals log of T2 over T1. And if you use logarithmic properties, you can calculate, you can put that in this form. So you have P2 over P1 to the power R over Cp equals T2 over T1. So for an ideal gas, you know that R equals Cp minus Cv. And by the way, the prime on the T2 is a reminder that this is an adiabatic quasi-static reversible process. So remember, it's changing very, very slowly. And you can substitute for gamma. So you have T prime 2 over T1 equals P2 over P1 to the power gamma minus 1 over gamma. And you know your gamma rules and your power rules by now. That's pretty much the theory behind this part, the open systems. You guys seem very sleepy and bored.